Pick up where we left off. We had just finished number 66. So that's 67 coming up. Which of the following processes represents the ionization energy of bromine? Remember how to write ionization energy. Now, I assume since all the answers have elemental bromine, that this is the first ionization energy. So if you start off with bromine, what phase must it be in? Gas. It has to be gas. Then we add a certain amount of energy. It has to be gas because if it's liquid or solid, it takes some of that energy to convert the phase from solid to liquid to gas. And we just want the energy it takes to promote an electron to infinity. So that means we're going to a +1 charge gas and that free electron. So that would be the expression of first ionization energy for bromine, which is C in our answers. All right. E8. Order of the elements: sulfur, chlorine, fluorine. Sulfur, chlorine, fluorine. Increasing ionization energy. Okay. So when we look at the periodic table, bit like that, this, that, and then we have hydrogen up here and helium up here. Ionization energy increases from lower left to upper right, or from left to right and from bottom to top. So let's see where these three are located relative to one another. Sulfur, chlorine, fluorine. Chlorine is to the right of sulfur. So this one should have a higher ionization energy than sulfur. But fluorine is above chlorine, so they're in the correct order as written. Okay. Let's see, 69. I have a suspicion we're going to need to leave that stuff up there. Increasing atomic radius. Okay, how does atomic radius vary? The atomic radius decreases from left to right and decreases from bottom to top. So this radius decreases from lower left to upper right, as long as we're staying in here in the representative elements. Once you get into the transition elements, things kind of go up and down. So put these in order of increasing atomic radius. Well, increasing atomic radius would be to the left and below. So actually, it's a reverse trend to this one. It should be that, that, and that. Just the opposite. Okay. All right. Let's see. 73. The following elements, which has the lowest first ionization energy? All right, so we got to find out where they are relative to one another. Barium is way down here. Oops. This is increase ionization energy. So barium, let me fix that. Barium is way down there, and calcium is up here. Yeah, it's right underneath that. Okay. And silicon is over here underneath carbon. And phosphorus is over here underneath nitrogen. It's next to silicon. And then chlorine. Chlorine is to the right. Well, except for the noble gases. Okay, now what's the question? Lowest first ionization energy. Lowest would be over here on this end. Barium would have the lowest first ionization energy. Okay, which is most likely to form a negative ion with charge 1-. Same elements. All the halogens form -1 ion. Okay, that's the only halogen in there. That was 74. Got that one all the way. 75. Which of the following atoms has the largest ionization energy? All right. Well, let's see. Oxygen would be over here. Lithium would be about here. Neon. Oh, I think we found it. Noble gas is going to have the largest first ionization energy because the electrons being removed from a noble gas are core electrons. It doesn't have any valence electrons. Right, so that was kind of a trick question. Recognize that all of its electrons are core. So it's going to have the highest of all of them. Okay, 77. Which has these types of electromagnetic radiation arranged in order of decreasing frequency. We want to decrease the frequency in order. So decreasing frequency is a decreasing energy. That's the way I look at it. It's easier for me to visualize decreasing energy than it is decreasing frequency. So of all those that are given, the highest energy one would be, I see some gamma. So gamma is going to be the highest energy. And that's the Greek letter for gamma. Well, let's just put them in order. X-ray, like gamma, X-ray, ultraviolet, visible, and that could have several in there. Then ultraviolet, visible, infrared, and then microwave, and then radio. Okay. So this is decreasing frequency and decreasing energy. Both. So if I do it that way, then I don't have to think about it. I just say, all right, which one fits? Well, let's see. Visible to ultraviolet. Oh, going the wrong direction. Radio to visible. Radio to visible. Nope, going the wrong direction. Ultraviolet to visible. Ultraviolet to visible, okay. And then to infrared. C looks good. Since we don't have any wonky ones in there, I mean, once you find the right answer, you can move on. So C would be our answer. Right. Scroll a little bit. 78. Which has these types of electromagnetic order of increasing wavelength. Decreasing frequency and increasing wavelength are the same thing. as far as order goes, right? Because C equals frequency times wavelength. So if this one, if we want decreasing frequency, increasing wavelength, because they're inversely proportional. So it's the same answer. Gives you the same answer. Decreasing energy. Same answer. Like I said before, when you decrease the frequency, you decrease the energy because of Planck's equations. Oops, sorry. Planck's equation. Decrease the frequency, decrease the energy. Okay. So we got 3 in a row with the same answer. Number 80. Let's see, this was 79. 79 was also C. And I'll just put 80 up here so that one can stay for a couple of minutes. In the quantum theory, the magnetic orbital momentum quantum number is most directly associated with which property of orbitals? All right, so our let's move it over. It's a little more room. Our quantum numbers are the principal, right? Then we have the not the magnetic. The magnetic is this one. L is the anybody remember what it's called? Oh my goodness. It's terrible to get old. Okay, here we go. Angular. Why can't I remember that one? The angular momentum. So this is principal. This is angular. This is magnetic. And this is spin. Okay, principal is energy and size. Angular is shape. Magnetic is orientation. And spin is just spin. Okay. As far as what they roughly stand for. So M sub L is orientation. That. If I just look at the next question, I would have got it right. Did y'all notice that? Or are you just sitting there waiting for me to find out? No? Okay. I've had students sit out there and just kind of giggle to themselves. Your instructor can't remember something. Okay, so the angular is shape. That would be D. This is 81. This is 80 here, and this is 81 here. Okay. All right. Let's see. I think we can fix this now. Eight, 84. Yeah, 84. Man. 84. Select the correct electronic configuration for copper. Okay, what do we need to know? The Z number, the atomic number, if it's neutral, right? So copper is 29. 29 electrons, 29 protons, 29 electrons. Now, in this, and you look at the potential answers, this is the abbreviated version. So you can start with, go to copper and go backwards until you get to the next lowest noble gas, argon, 18.
Let me just leave these here on the table.
Yeah, that's fine. Okay, once you get to argon, then what's next? Well, this is principal quantum number 3, this is principal quantum number 4, 4s2. And then you're going to go across the transition metals with a 3D. 3D takes you up to 1, 2, 3, 4, 5, 6, 7, 8, 9, 3D9. Okay, here's the problem. This is one of those anomalies. In order to follow the Aufbau principle, we have to put electrons in the next lowest orbital in terms of energy. This is not the correct arrangement for the next lowest orbital, because how many orbitals does D have? It has 1, 2, 3, 4, 5. The most stable arrangement for any of these sublevels is to have 1 electron in each orbital or 2 electrons in each orbital, completely filled. Then it stabilizes the subshell. Right? So in order to do that, right, we're closest to putting 2 in each one. Right? And to do that, what we have to do is we have to steal 1 from the S to make that 10. Okay. So copper's like that, and 1, 2, 3, 4. Chromium is like that also. Well, while we're here, I might as well show you chromium too. Chromium is, let's see, 24. So we would do chromium with argon core. At that place, 18 from 26 is 6, right? So instead of putting 2 here and 4 there, we put 1 here and 5 there. That makes 1 in each orbital. That's more stable than 2 here and 4 there. Okay, that's another anomaly. And these occur periodically in the transition metals and even in the lanthanides and actinides that do that. I think that's the reason I chose this one, just because we didn't cover it in class. I may have mentioned that there are certain oddball structures in there, but we didn't go over any of them. And this is one of them. Okay. 25. Just asking myself a question for a second. Okay, which of the following equations correctly represents process involved in electron affinity? Okay, so for electron affinity, and we're using a generic symbol this time. So you always start with a neutral gas atom. And if it's diatomic, it has to be split apart. Say if it's oxygen, it has to be 1 oxygen atom. We have to add enough energy to put everything in the gas phase, plus break apart any multiples. Diatomics are usually the case. Once you got that, then electron affinity says we get an electron added to that one. And that produces a gaseous anion. So that's C. Okay. Right. 86. Let's see. Atomic radius. Well, maybe I shouldn't have erased my periodic table after all. Which of the following atoms are arranged in decreasing atomic radius? Okay, well, let's see what we got here. Lithium, oxygen, nitrogen, fluorine. Okay. Sodium, strontium. Sodium and strontium also. Strontium. Sodium. And calcium, cesium. Calcium. Cesium. Sulfur and selenium. All right. Atomic radius. Which one of these would be the smallest one? Up there, upper right. So that's the smallest. And we want all the carets are to the right, except for the bottom one. That's a trick. It's reversed. And that actually that shouldn't even be allowed because the question says decreasing atomic radius. Right. So E is increasing. As it turns out, E is not the answer anyway. Okay, so let's say which one's the smallest one? Fluorine. Put fluorine over here. It's the smallest radius. Okay, what's the biggest radius? Let's see, probably cesium, lower left. Yeah, cesium would be the, oops. Cesium would be the biggest one. Okay, now let's fill in the gaps. Let's say from fluorine, if we stay in the same period, then we should be able to move from left to right. Because when you go down to the next period, you're adding another level, another shell, which automatically increases the size. So if we go from fluorine and we work for the ones that are next to fluorine, oxygen would be next, right? And then do we have a carbon? No carbon. Oh, we have a nitrogen. Like that. Okay. So that takes care of that one, and this one. And anybody else in that list? Carbon, boron, beryllium, lithium. Lithium, okay. There we go. There's that one. And then if we move down, let's see. There's no chlorine. Sulfur. We got sulfur. Yeah, sulfur. Selenium is bigger than sulfur. So let's hold it off down here. Because it's below selenium. Anybody else in selenium's period? Phosphorus, nope. Silicon, nope. Aluminum, magnesium, sodium. Sodium's there. Okay, then we go down one. And let's see. To the far right, we have bromine, selenium. Okay, so now we have selenium. You see what I'm doing? If you don't, stop me. Selenium. Okay, arsenic, germanium, gallium, nope. Keep going across. Calcium. Yeah, calcium. All right. And cesium. There we go. So that should be the order of decreasing radius. Now, we have any that fit in here? A won't work because nitrogen's flipped with oxygen. Lithium, nitrogen, oxygen. Okay, that one works. This is B. I guess we're done. Because C has these two flipped the wrong side. Sodium. Oh, strontium. I forgot strontium. Let's be down here. There we go. It won't matter. If we do, look at the bottom one. Selenium, sulfur, they're in the wrong order. Okay, so we found our answer. So I used left to right and top to bottom as separate introductions to the various elements that were given. Okay. If you understand the trends, then this is fairly logical. 87. Consider an atom traveling 1% of the speed of light. The de Broglie wavelength is found to be 1.46 times 10 to the minus 3rd picometers. Which element is this? All right. Let's see. We haven't talked about the de Broglie wavelength, have we? Unless you've actually gone into the problems and looked up how the answer was determined. We're given a velocity, right, which can be equated to a mass. We're also given a velocity that can be equated to energy. Now, we're not going to introduce the de Broglie equation here. That's a little beyond us, but I hope we can rationalize what do we need to know to find the element. I don't think we can get from this information, we can get the atomic number of protons. I don't see any route to the protons, but we might be able to get the molar mass. Okay. So if we've got one atom traveling at 1% speed of light, then we would take Einstein's equation and substitute the velocity of this is the relativistic velocity of the particle. And that would, then we need to know the energy. If we know the energy, we know the velocity because it's 1% speed of light. We need to know the energy, then we can find the mass of one atom. Okay. So how would we do that? Well, there's another Planck's equation says this, right? Do we know the wavelength yet? Let's see. Oh, okay, we're going to combine them. All right. Let's see. Mass velocity, frequency. What else are we given in there? We are given the wavelength. Okay, that's why this needs to be solved from wavelength. So C equals frequency times wavelength, and wavelength equals C divided by frequency. So now we can put E equals H C over, oops. Yeah, that's right. Is that right? No, that's not right. I solved the wrong one, didn't I? C over wavelength. There we go. C wavelength. Okay. Now, the energy is going to be the same in both circumstances. So if we say equate this, if A is equal to B and B equals to C, then A equals C. So those are equal because they're both equal to the same energy. That means M velocity of that particle equals hc over lambda. Okay, what we want to know is the mass. So I want to solve for mass. hc over lambda b squared. So there's our equation to get the mass of one atom. If you know the mass of one atom, you can equate that to, you can ratio that to a mole of atoms, and that's a mass per mole, which is the molar mass. Okay, Did I lose anybody? Okay. All right, so. Well, let's see. We're not talking about light now. We're talking about the velocity of this particle. So actually what we got here is V, V, and V. The velocity of the particle, not the velocity of light. Because we're not talking about light. We're talking about a particle that's accelerated to 1% of the speed of light. So now we can get rid of that V. That's h over lambda velocity, because this one cancels one of those. Okay. So what's the Planck's constant? I think I remember 6.626, is it, times 10 to the minus 34 joule seconds. What's the wavelength? Well, the de Broglie wavelength is 1.46 times 10 to the minus 30 picometers. 1.46 times 10 to the minus 3 picometers. This has to be in meters in order for this to work. So what's pico? What's the prefix pico mean? Nano means 10 to the minus 9th. Pico means 10 to the minus 12th. Okay, so it's 10 to the minus 3rd times 10 to the minus 12, which is 10 to the minus 15. 1.46 times meters. So now we have 1.46 times 10 to the minus 15 meters. And velocity then will be 1% the speed of light. Right? If C equals 2.9979, is it? Times 10 to the 8th meters per second. Then 1% of that would be, we take 2 of those away. What? Tens, hundreds. Times 10 to the 6th meters per second. That's what the velocity is. Or if it makes you feel better, you can just say, all right, what's 1% of that? Well, 1% equals 0.01 times. And that's 1 times 10 to the minus 2. So that's why we get 6. 9979 times 10 to the 6th meters per second. And let's see if our units work out. Meters. Let's see. The answer is going to come out in kilograms. And that's because, okay, see this energy unit in here? Joules is kilogram meters squared per second. Kilogram meters squared per second squared. Kilogram meters squared per second squared. This is what I was talking about early on. When you need to cancel units, you got to know what these things are equal to. Otherwise, you just have to say, okay, this thing is going to give me SI units, and the SI unit for mass is kilograms. Okay, but that's why it's kilograms, because of this conversion. Okay, so it's right. It just took me a minute to realize. All right, let's see if the math works out. 6.626. Okay, and then 1.46 exponent times 15 and 2.79 exponent 6. This is 1.51 times 10 to the minus 25 kilogram, and this is for 1 atom. So how many grams would that be? If the units get bigger, No, the units are going to get smaller. Excuse me. Units get smaller, the number gets bigger by a factor of 3, orders magnitude 3. So that'd be minus 22. Okay. So 1.51 times 10 to the minus 22 grams. And then, so I've got those. That was 10 to the 23rd. Atoms per mole. Atoms cancel, that gives us moles. So I just need to multiply that one by 6.022 23rd. And that's fraction. Something's not right. Okay, I did something wrong in my calculation. Oh, I know what I did wrong. There it is. I forgot, in my calculator, I forgot to change from kilograms to grams. So once I fix that, then the molar mass is 91.2 grams per mole. Okay. 91.2 grams per mole. What is that? Zirconium. Okay. That's a lot of work, one little answer. But it's true. When de Broglie proposed that all matter has a wavelength, some physicists thought he was nuts. Not all of them, some of them did. But eventually they came around. Why? Because it works. Okay, let's see. How about 88? I chewed up a lot of time there. Investigation of the electronic absorption spectrum of particular elements found that a photon having wavelength 500 nanometers, given the wavelength, 500 nanometers, okay, provides just enough energy to promote an electron from the second quantum level to the third. From second to the third. So we've got an electron going this way. Right there. With that much energy. From this information, we can deduce the energy of the n equals 2 level. No. What does this tell us? This tells us the change in energy. It's at one energy level here with a certain amount of energy, and we add this much energy to get it from here to here. That's a change in energy. That's not the absolute value. So B is also wrong. The sum of the energies? No, the difference in the energies from N2 to N3. That's one, the D. D is the answer. It's the difference in energy. Right. 89. And might be 90 also. The next two questions, yeah, 89 and 90 both. Use that the energy values for these orbitals. Okay. 89 asks what? In the hydrogen spectrum, what's the wavelength of light associated with N3 to N1? So if it's going from 3 to 1, gonna give up a certain amount of energy. All right, how do we find that out? Well, the change in energy is equal to the absolute energy of E equals final minus E equals initial. So we just need to read that off of the final is minus 2.178. 178 times 10 to the minus 18 joules. And subtract the third one, which is 02420 minus 02420 times 10 to the minus 8. Okay. So this is going to become a positive. And if we do it like that, 2420, that's 0. See, it line these up. Okay, 6, 3, 2 from 11 is 9. Times 10 to the minus 18 joules. All right, so they're asking for the wavelength. All right, if this is the energy, now this transition, we don't need the negative sign to do the calculation for Planck's equation. We are looking for wavelength though, so we want C over wavelength. And then we want to solve for wavelength with the wavelength over here. And put the energy over here. We only need the absolute value because the transition does the same thing. If it goes the other way, it's absorbing. If it goes this way, it's emitting. We just need the absolute amount of energy. So Planck's constant in minus 34 joules second. And speed of light is 10 to the 8th meters per second. And then energy in joules, 1.9360 times 10 to the minus 18 joules. In this case, joules are going to cancel and seconds will cancel. So we'll get our wavelength in meters. All right, and then the speed of light times, and then our energy. This is meters, 1.03 times 10 to the minus 7 meters. Our answer is in nanometers. So what we need to do is say, all right, if we take this number, all right, let's do it this way. I think it'd be easier to understand. Trying to do it in your head. So how many meters? How many nanometers in a meter? 10 to the 9th nanometers per meter. So the meters cancel, and this becomes 1.03 times 10 squared, or 103 nanometers. And that's not, yeah, there it is. Oh, it's in meters. Okay, so there it is. I bet you saw that one coming. Okay, so now let's see, do 90. Okay, what's the wavelength of light that is emitted when an excited electron in hydrogen atom falls from N5 to N1? In this case, the final value is minus 2.178. Energy then equals minus 2.178 times 10 to the minus 18. Yeah, 18 joules. And subtract the initial, which would be the level 5. Oops. There it is. 0.08712. 2 times 10 to the minus 18. Okay. So 2178 and 0.08712 is going to be 8 and 198. So 0. 2.0988 times 10 to the minus 18th joules. And that's equal to Planck's constant times frequency. I'm going to do this in 2 steps. 2.0 exponent 15. And then I'm going to divide by this. Right, solve for that. That means this comes over here in the denominator. And that's frequency equals 3.156 hertz. And if we want to find wavelength, we just say wavelength, equals speed of light, 9979 times 10 to the 8th per second, divided by 3. Oops. That makes a big difference. I forgot my exponent. 156 times 10 to the 15th. And that's reciprocal seconds. So, did I do that right? C equals, yeah, it should be right. That's not canceling, is it? Let me see what I get. I get 9.50 times 10 to the minus 8 meters. I don't think it's right. Well, that problem says it's right. It's just that hertz and frequency are reciprocal seconds. Oh, okay. So that's like saying 1 over seconds here, right? The seconds cancel. Okay, we're good. I'm overthinking these problems. So the answer for this one is B, 9.50 times 10 to the minus 8 meters. '91. Which of the following is reasonable criticism of Bohr model of the atom? Okay. It makes no attempt to explain why the negative electron does not eventually fall into the positive nucleus. Reasonable criticism. Well, that is a problem with the Bohr model, but the Bohr model just assumes that it doesn't. It doesn't try to explain it at all. So if it doesn't try to explain it, then you can't criticize it for something that it's not claiming. That's why A is not an answer. It doesn't adequately predict the spectrum of hydrogen. Well, it does. It does not adequately predict the ionization energy of the valence electrons for elements other than hydrogen. Well, that's true. Right. It does not adequately predict the ionization energy of the first energy level electrons for one electron species for elements other than hydrogen. Well, it does with the formula. If you have a hydrogen-like atom with only one electron, and it can have as many protons as it wants, then that factor, the factor over here, the z squared over n squared factor, all you have to do is be sure that this one is the number of protons and that one is the energy level. But it has to be hydrogen-like, that is only one electron. So anything else but hydrogen has to be an ion. And a positive ion at that. All right, so C's the best answer. How about 93? Which of the following statements are true? Well, let's see. An excited atom can return to its ground state by absorbing electromagnetic radiation. If it returns to its ground state, it's going to give up radiation, not absorb it. All right, so 1 is false. About 2. The energy of an atom is increased when electromagnetic radiation is emitted from it. Well, that's wrong too. It's decreased when it gives up that energy. Right? Yeah. The energy of electromagnetic radiation increases as its frequency increases. Yes. We know that was true from Planck's constant. Planck's equation. They're directly proportional. An electron in the n equals 4 state in the hydrogen atom can go to the n equal 2 state by emitting electromagnetic. Yeah. That's true. And the frequency of the wavelength of electromagnetic radiation is inversely proportional to each. Frequency and wavelength are inversely proportional. Yes. There we go. So, oh, we got 5. Almost skipped 5. I did skip 5. This one's true. That's 4. I skipped 4, didn't it? No. That one needs to be down here. I skipped 3. What's 3? The energy of electromagnetic radiation increases as its frequency increases. Well, that's true. What's different in 4? The electron in an N4 by emitting electromagnetic radiation. Yeah, that's true. 3, 4, and 5 are all true. Yep. So that's D. 94. Consider the following representation of a 2p orbital. Does that look accurate? Yeah, remember the p's. X, Y, and Z. You go like this, that, this. So they're oriented either on the x-axis, y-axis, or the z-axis. So yeah, that's a p orbital. They're telling us it's 2p orbital. That's fine. Which of the following statements best describes the movement of electrons in a p orbital? The electrons move along the outer surface of the p orbital. No. What are we saying with the orbitals shapes? We're not saying we know exactly where they are. We're saying that it's highly probable that these electrons are in somewhere in there, in that region. It's statistical. So if there's any claim that we actually know how they're moving, then that's false. Electrons move within the 2 lobes, but never beyond the outside surface. No, probabilities, you still have a small probability that they could be outside that orbital. That's like a 95% probability they're in that space. But that other 5%, they could be out here somewhere. C, the electrons are concentrated at the center node of the two lobes. Well, that's false on its face because we're saying you don't find electrons at the node. There's no probability that electrons are at a node. Electrons are only moving in one lobe at any given time. No, they're spread out all over as far as we're concerned. Electron movement cannot be exactly determined. That's the one. We can't say where the electrons are because we're more interested in their energy. According to Heisenberg's uncertainty. And this is, I'll give you that instead. And it has to be greater than or equal to Planck's constant over 4 pi. So if we knew exactly where the thing was, we would know what its energy was, and that wouldn't help us at all. It's more important to know the energy than it is the position. Okay, 95. How many electrons can be contained in all of the orbitals with n equals 4? You should be able to do this one. N equals 4. Okay, so what can L be? L can be 0, 1, 2, or 3, right? Okay. M's of L's. For this one, there can be a 0. For this one, there can be a -1, 0, +1. For this one, there can be a -2, -1, 0, +1, +2. And for that one, there can be a -3, -2, -1, 0, +1, +2, +3. That's all the orbitals possible. So we have what? 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 16. 16 orbitals are possible. Oops. Oh, how many electrons? There you go. Because each one can have 2 electrons, spin up, spin down. Better read the question, that helps a lot then. All right. '96. The small but important energy differences between 3s, 3p, and 3d are due mainly to what? This goes back to that description of the penetration effect. They're all at the same principal quantum level, 3, which means they're in the general area, the general energy domain. But they do have slight differences. So 3D is going to be like this is energy, and this is distance from the nucleus. So the 3D is going to be like that. And the 3P is going to have a kind of a hump out here like this. Like that. And then like this. And then the 3S is going to have a hump here. And here. And here. So this is the S, this is the D, excuse me, this is the P, and this is the D. And the slight differences are cumulative, additive, so to speak, of these penetration effects. Right? S, even though the major energy component for S is further out, it does penetrate closer to the nucleus. And that gives it a slightly lower energy, which is why the 3S fills first, then the 3P fills. But then if we stick a 4S in there, the 4S is going to penetrate in front of the 3D. And it's gonna have a component down here below the D, the 4s. So 4s comes first, then the 3D. Okay, so the penetration effect answers that question. 97. Which of the following was not an elemental property usually predicted by Mendeleev as for unknown elements? Electronic configuration. They had no idea of subatomic particles. They just knew masses. And then with Avogadro's introduction of his theory, well, actually, his student introduced his theory. Then they had a handle on how many atoms, but they didn't know anything about the internal structure of the atom. So atomic mass, yeah, density, boiling point, oxide formula, all those were things that Mendeleev introduced as characteristics of the elements in his table and used to predict undiscovered elements. But the electronic configuration, nope, had no idea about that. 98. Which of the following atoms are or ions has 3 unpaired electrons? Okay. Well, let's see. Well, let's start at the top. Structure for nitrogen, 7. So we have 1s2, 2s2, 3. Oops. 2p, 3. Looks like 3 unpaired to me. Because these, the S's, are going to be paired already. All right, we found our answer. I mean, if you want to, you can draw the rest of them out. We're kind of short on time. But that's how you answer it. You draw the structure. 101. And element E has the electronic configuration. Okay. Some element has the electronic configuration. What is it? Krypton? 36. I think, yeah. 5s2, 4d10. 5s2, 4d10, and 5p2. Okay. What's the question? The formula for the fluoride. All right. So if we combine this one, we assume it's a metal because they're combining it with fluoride. And we can prove it's a metal. We need to know how many fluorines. If we go to the level 5, which is the highest, it has 4 valence electrons. And if we go 5s2, and then 4d10, that's 10. So it could possibly have one of two different. If we lose 2 of these higher, these are slightly higher energy than the S's. So if we lose those 2, then we have, all right, we have a 2+ here and a 1- there. We need 2 of these. That's a possibility. If we lose all 4 of them, then we would have 4 fluorines because this will be 4+, and we need 4 of those. So you look for your choices, EF2 or EF4. There's no 2, but there is a 4. Right. So process of elimination, you get B. 104. Are we getting close? Oh. I know there's one at the end that just it takes some real brain power to do it, so we might have to skip that one. Which of the following atoms would have the largest second ionization energy? All right. So second ionization energy, if you've got any that are digging down into the core, then that's a good candidate. Chlorine's first ionization energy is going to make it look like sulfur. And second is going to make it look like phosphorus. So that's not a good candidate. Magnesium, you can take away your second electron from a valence, right? So magnesium wouldn't work either. Sulfur, right? Phosphorus, silicon. You're still taking away valence electrons. It's no big deal. Calcium, same as magnesium. You've got 2 valence electrons to play with. Sodium, you've only got 1 valence electron. Once you get rid of that one, then you're into the core. Sodium's your answer. All right. 107. Which of the following concerning second ionization energies is true? The second ionization of aluminum is higher than that of magnesium because magnesium wants to lose the second electron, so it is easier to take the second. All right. If we're comparing aluminum and magnesium for all of these questions, aluminum has 3 valence electrons. Magnesium has 2 valence electrons. First ionization energy for aluminum is higher than magnesium. So second is probably higher also. Okay. Now, if we get to third ionization energy, then magnesium is going to jump up way above aluminum. So that's a possibility. The second ionization energy of aluminum is higher than that of magnesium. Well, yeah, it should be. But what's the reason? Because magnesium wants to lose the second electron, so it's easier. No, it's because what governs the trend in a period? It's the nuclear charge, the number of protons. So A doesn't explain it. I mean, it's a true statement, but it doesn't explain it correctly. Aluminum is higher than that of magnesium. This is B, because the electrons are taken from the same energy level, but the aluminum atom has 1 more proton. Yes. Right. That explains it right there. We found our answer and there are no squirrely ones down there, so we'll stop there. B's your answer. All right. Oh, I'm out of time on it. Is that right? 45. I don't know if I can do this one in 5 minutes. Consider a planet where the temperature is so high that the ground state of an electron in a hydrogen atom is N equals 4. It's like on Venus. What is the ratio of ionization energy for hydrogen in this planet compared to that on Earth? So the ratio of the ionization energies, 108, is the ionization energy. Let's get them in the right order. Okay. The ratio of the ionization energy for the exoplanet compared to the ionization energy for Earth. Okay, that's the way we would do it. Now, we can look at this qualitatively. Since this one is starting from N equals 1 up to infinity, this one's starting from N equals 4 up to infinity. So which one's going to take more energy? That right there. So the ratio is going to be that's small and this is large. So if you look at your answers, you have one, they're not going to be equal. So E can't be it. So it's either A or C. So you can eliminate the rest of it. Because it's going to be small, large. Now, the calculations that you're required to do to get there, I'm tempted to say there's a relationship in there of n, like n squared for this one and n squared for Earth. And if we ratio the equations, we get an n squared over n squared, which would be, this would be, well, actually, it would be reverse of that. Because if we put n squared up here, it'd be 16 over 1, and that's the wrong ratio. So you'd have to flip it to 1 over 16. The answer is 1 to 16. But the way I work it out in work problems, I actually do the energy calculations. And let's see, I think I might be onto something there. I just have the ratios incorrect. Yeah. Okay, so let's look at it this way. If we have this energy, and these energies are equal to that constant value, right? That big long number, right? Times z squared over n squared. So if we ratio those two, because this is going to be XO and this is going to be Earth, right? Well, z's are going to be the same. This is going to be XO, and this is going to be Earth, right? This is equal to 1, and this is equal to 1, right? This is in the denominator of the denominator, which means it's in the numerator. So n squared over the Earth over n squared of the exoplanet. Okay. And since they're all related to infinity, then this one starts at 4 and goes to infinity. So 4 squared and 1 squared equals 1 to 16. The ratio is 1 to 16. That's the quickest way to do it. You can actually do the calculations, right? And that's what I did in the work problems. And you'll get 1 to 16. I guarantee it. But this works quicker. And if you were taking a timed test, like a standard American Chemical Society test nationwide, and they give it to, I knew a Concord professor that used to use that one for his chemistry students because it would give them an idea of where they were in the nation. Then you'd want to use the quicker way to get there. Okay, I believe that's the last one, isn't it? Yeah, that's it.